What's up, folks? So last we left off, I derived the objective function for stable diffusion XL. And, I had done all this work building all the components and deriving the objective function. And I was going to code up DDPM and do some coding for SDXL. But honestly, I want to move on to the architecture for stable diffusion 3. I want to build. I probably won't be able to actually build Stable Diffusion 3 because their architecture is still closed, but I want to start experimenting on the frontier of the technology that Stable Diffusion 3 is based on, which is rectified flow and diffusion transformers. So essentially rectified flow for image generation. So rectified flow is different than diffusion training. And so basically this next series of videos, I'll put it under a different playlist, is going to be the rectified flow playlist. And it's going to give you everything you need to understand rectified flow. So in order to do that, I want to describe the lineage of rectified flow, which will help you it'll give you more of an intuitive understanding of what flow matching is and what data transport is. Because essentially what rectified flow is a form of data transport. And so I want to start with discrete normalized flows and then move to conditional normalized flows and then move to flow matching and rectified flows. And that's essentially what you'll find when you read the papers. So let's start with discrete normalized flow today. I'm not going to do any coding for this. I'm just going to spend one video, showing you what discrete normalized flows is on my iPad, explaining the maths so that it'll help you get an intuition for the space. And then I'll spend one video doing continuous normalized flows, and then I'll move on to deriving the objective function for a rectified flow and start building some models. So I think within 3 videos, we can be actually coding some implementations. So let's get started on discrete normalized flow. Okay. This is the paper where discrete normalized flow was introduced. It's the seminal paper, Variational Inference with Normalizing Flows. And it actually uses it. Essentially, you are creating, in variational inference, when you create this approximate distribution Q in order to get your evidence lower bound, in efforts to create a more complex approximate Q, the authors introduced what's called normalizing flows to basically create this more complex Q. Discrete normalized flow became a technique in and of itself as opposed to just an auxiliary for variational inference. Okay, so I'm gonna start my iPad up. So I'm not gonna do any formal proofs in this. I try to stay away from formal proofs unless it helps us get more of an intuition on the math. The math that I usually show it's not proofs. It's more so even the derivations that I do. I guess you could call them proofs, if you will, but it's more so just to help us get an intuition on the math. Okay, so let's get started. So rectified flow series, discrete normalizing flows. Okay, so imagine we want to turn a simple distribution into a more complex one. Okay, so this is our simple distribution over here. I'm just drawing shapes because you can think of distributions as volumes, right? Volumes containing mass, containing probability mass. Say this is a Gaussian, okay? So let's just define the variables. Okay, so the goal is we want to turn a simple distribution into a more complex one. And say we have these invertible maps F all the way to F sub capital K, where all of these maps basically take a Zi minus 1 and go to Zi. So, F2 goes from Z2 to, F2 goes from Z1, is a map from Z1 to Z2, and so on. We'll say X in Z naught, X equals Z naught. Those are both our image. I'm using Z naught because it's just going to follow the rest of the Z's, right? and then z sub k is, so both of these, so z naught and z sub k, x, z naught, and z sub k are all image vectors, and z sub k is a standard normal, a standard Gaussian, and p of x and p of z are probability density functions. They're PDFs. Okay, so we have a sequence of invertible transformations, f, okay, such that when we apply them all to x, we get a standard normal. And then, so this is training. This is what we're going to do during training. This is the forward pass. This is the forward pass. And then this is inference down here, where this is why the maps have to be invertible, is because we simply apply the composition of the inverses to z, and we get an image. Okay, so essentially what we're doing is, so essentially during inference, we take a simple distribution and we just pass it all through these invertible maps till we get a more complex distribution. Now, essentially the objective function is to maximize this likelihood or to minimize the negative log likelihood, as it is with most machine learning objectives. And it's described by this equation, which is called the discrete change of variables formula. So you can see here is our assumed Gaussian, our assumed standard normal, okay? And we start with that, and we essentially add the sum to capital K. We essentially add the sum of I equals 1 to k of all of these we have the sum of I equals 1 to k of the determinant of the Jacobian. So these partial derivatives, so it's essentially the partial derivative of, so let's say we have f2 goes from z1 to z2. It's the partial derivative of f2 with respect to the variable z1. But remember, this is a map. These are maps from a vector space to another vector space. So it's the partial derivative of, this is a matrix that contains the pairwise partial derivatives of all the components of the output paired with all the components, all permutations of the input. And so basically what I'm going to do in this video is explain what this equation means. So, okay, so how do we get A? Specifically, what does this determinant mean? What does the determinant of the Jacobian mean? Right? The reason why I dove into this is because for myself, I wanted to get an intuition on what that means. So let's do a brief aside on probabilities and PDFs. So a PDF by itself is not a probability. A PDF is a probability mass per infinitesimal volume. Okay, so what that means is this gives us a mass per volume, and then you can consider dx to be an infinitesimal interval. an infinitesimal volume, or you can consider it to be an interval, such that when you multiply it by this density, you get a mass. Okay? So, and then recall probabilities. So I can't put in, I can put in 193. So like, let's say the random variable capital X is height, right? I can put in 193 here for like 193 centimeters, and I can get out a density. But if I try to get the probability of 193 here, it's 0. That's not the way it works. In order to get probabilities, right, you need to do an integral from A to B of the probability density function. Okay, so imagine you put in 193 here to the probability density function and you get 0.02. You can think of this as 0.02 mass per some kind of unit volume. So I just wanted to review that really quickly just to help get an intuition for what's to come. Okay, so let's move on to the Jacobian. A bit more scaffolding before we can fully explain what this means. So the Jacobian, so again, so say we have an f from an n-dimensional vector to a mapping of n-dimensional vectors to m-dimensional vectors. Now, in our case, n is going to be equal to m, okay? So moving forward, you can consider n equal to m. So say we have a mapping f that sends, a d-dimensional vector to another d-dimensional vector. What the Jacobian matrix is a linear approximation of your map f, your function f, around an infinitesimal space around a point z. So if we were to take a point z and draw a super tiny space around it, a neighborhood you would call it in measure theory, you take a neighborhood around z, an infinitesimal neighborhood around z, the Jacobian represents how that space is transformed by the map f. The Jacobian of f represents how that neighborhood z is transformed by f. And so it's a small linear approximation of the map f. It's a linear approximation of the map f. So that means that f of x plus delta x is approximately equal to f of x plus the Jacobian times delta x. And in 2 dimensions, you can see I have x delta x and then f of x and f of x plus delta x, right? So the Jacobian would be approximately equal to this point, or f of x plus the Jacobian times delta x would be approximately equal to this point. But remember, delta x, the larger delta x, since it's a linear approximation of a neighborhood, right? Of a small neighborhood around z, the bigger delta x is, the more of an error we're gonna end up somewhere that's just not close, right? So really, we want this delta x to be very close to x in order for our linear approximation to in order for this equation to actually yield correct numerically correct values. And so what the Jacobian actually is a matrix. It's a matrix of component-wise partial derivatives, right? So it's the partial derivative of f sub 1 with, it's the partial derivative of f sub 1 with respect to all of the z components in this direction. And it's the partial derivative of all the f components in this direction with respect to one of the one of the z components, z1 here. So that's how the matrix works. Yeah, this is better. Yeah, see, I have it correct down here. Yeah, this is better. Okay. Oh, right, because I copied and pasted this from another document that I was writing on. Okay, so, and then we can say it's from Z to X. And we're not really referencing X anymore. We're not really referencing X anymore here. Okay. All right, so the Jacobian is a component-wise. It's taking the partial derivative of F with respect to Z, and it's going to be component-wise because they're both d-dimensional vectors, okay? So it's the instantaneous rate of change of F with respect to all the directions. Okay, so, yeah, I already covered this. What the geometric meaning is, right? The Jacobian is a local linearization. It's a local linearization of a nonlinear map, right? Around some small neighborhood of Z, we're creating a local linear approximation of the function f. The determinant of the Jacobian, so the determinant of the Jacobian, which we find in our equation A, right, is essentially a volume scaling factor. It's a volume scaling factor. So say this is Z, this point, and then this is a small infinitesimal cube around Z. When we send it through F, it gets stretched and compressed into, it gets transformed into this parallelogram. Now, the Jacobian, which is a linear approximation of your map F around a small neighborhood, the determinant of that Jacobian determines how this volume has scaled from its original size. So if we have, now the reason why I'm covering all this is because, well, okay, so let me wait. So essentially the thing to know is that we have some cube defined around our point Z, some infinitesimal cube, and then after it gets mapped through F, it stretches or it compresses by, it's transformed into, in this case, it's this parallelogram. It's always going to be a parallelogram because we're talking about linear approximations, right? Now, so the reason why this is important is because there's something called probability conservation. If you think of this as a probability distribution, if you think of both of these as distributions, then if this is transformed into this, the probability mass has to be conserved. And so if the length of this doubles, right, then the density has to decrease by half in order for the mass to be conserved. And so we need to know how to properly scale between transformations so we can know how to properly conserve, how to calculate the proper, so we can know how to properly conserve the mass. And so one more thing I want to talk about before we get to the derivation of A. So I want to talk about area and the determinant as it relates to the Jacobian. So say we have a point Z right here, and then we have two displacement vectors, 0 dz2 and 0 dz1 and dz1 0, right? Such that, you know, dz1, dz2, right? This vector up here, all four of these together make a square. So we can describe this square by what's called two displacement vectors, these two displacement vectors, okay? And you can think of dz1 and dz2 are just two small deltas from the original points, which is 0, 0, okay? So these two displacement vectors make up our square. Now, if we apply a map F to these two vectors, right, and they get transformed, say these two vectors that make up this square get transformed into this parallelogram. We can describe the output, we can describe the two output displacement vectors u and v by these, so this is u and this is v. Well, actually, yeah, so this is u and this is v. So now let's say we want to know the area of this parallelogram. So the area of a parallelogram described by two vectors is this right here, which is equal to the determinant of u and v. So if we put u and v beside each other, right, it's this, right? We just pull the Jacobian out. If we multiply this Jacobian through, we just reclaim the original vectors, right? So it's described like this. And then if we take the determinant of u and v by this property of determinants, the determinant of two matrices, A and B, is the determinant of A times the determinant of B, right? So we just bring the determinant out, or we just distribute it, I guess, across multiplication, if you will. And then the determinant of this, right, we have this times this minus this times this, right? So it's just dz1 times dz2, right? So the area of that parallelogram is equal to this, okay? So remember that property. So essentially, what we're doing is we're showing you, basically what this means is we're taking dz1 and dz2 are our two original displacement vectors. All we're doing is taking, right, because remember, I'm trying to show you that the determinant is, how did I describe it? A volume scaling factor, right? The determinant is a volume scaling factor. It's not the actual volume, it's a volume scaling factor, right? So if these are our two original vectors in Z space and of a square, so we know the area of a square, we just multiply them together, right? If we want to know the area of the parallelogram, we just multiply the original area times this volume scaling factor. And if that's a distribution, right, we can already see how we're describing probability mass. Okay, so now let's get back to how do we get A? How do we get this equation? Let me change these variables. Yeah, okay. Okay. So how do we get this equation? So the change of variables theorem, basically this is probability conservation that I was describing. For any measurable set A, right? So, and this is the inverse. This is basically applying the inverse map to A, right? So this is just describing this space is just applying the inverse of F to A, and so it's a different space. It's a different. It's a post transformation space. So essentially, it's saying if you integrate over an interval. If you integrate over an interval to get a probability mass, if you apply an inverse map to that interval and try to get the density in that space, it has to be equal, right? It's saying that mass cannot be created or destroyed. It can only be transformed. So what if we shrink these, whatever interval is defined here, what if we shrink it down to an infinitesimal interval, right? So if we do that, we remove these integrals, right? So the integral is not relevant anymore. We're basically saying that this is approximately equal to this. So we just set them equal, right? Again, I'm not doing formal proofs. I'm just trying to give you an intuition. So just remember this. We're going to use this. So let's take the 2D case. So same problem setup. F is a map from Z to X, right? So F of Z equals X, and Z is some, Z and X are both two-dimensional vectors. X and Z are both two-dimensional vectors. So a little square patch in Z space maps to a parallelogram in X space. Okay, just like here. Okay. A square patch maps to a parallelogram in X space. All right. So remember, we defined this above, right? We showed how the area of the parallelogram can be described as the volume scaling factor times the volume of the original cube, right? So now I just divide. Okay, so I divide dx by dz, and then you invert it to get this, right? So now remember probability conservation. We described up here. Now it's in 2 dimensions, so we're just doing dx1 and dx2, dz1, dz2, right? You have to include both components. So now if I divide dz by dx, if I just divide both sides by dx1 and dx2, we get this, right? I just substitute it to get that. So now P of x is equal to P of z times the inverse of the determinant. Okay. So remember that. So just did some algebra. I'm saying the probability density of x is equal to the probability density of z times the determinant. Times the determinant of the Jacobian. So in higher dimensions, we just have more components, but this is going to stay the same. This is going to be the exact same. Okay? So the math stays the same. Again, I'm not doing measure theory proofs. I'm just showing you the intuition. So the general formula is this. P of x equals P of z times the determinant of the Jacobian of f. So now back to discrete normalizing flows. So the question is, how do we get A? How do we get this equation? Okay. So again, we have our data, and then we have our Gaussian, our simple standard normal here. How do we get this equation? All right, so we have our general formula, right? So I'm just going to basically expand the recursion. So I'm going to say P of Z1, right, is equal to the Jacobian, so the partial of F1 with respect to its input, right, based on this, okay? Then I say P of Z2 is equal to this, and then I'm just going to keep going down the line. P of, Z3 is equal to, and I'm going to keep expanding it out, and then I substitute. P of Z1 is this. So if I substitute that in for this right here, and you just keep expanding it out, right, you're going to get this product. Now, P of x is equal to P of z. So we can already see how it looks. We just bring a log through, right? And it starts to look like this. But we have P of x and P of z on different sides. Remember, P of x is P of z naught. So P of x is z naught. So basically what we do is we just divide by, just divide both sides by this, right? Or sorry, multiply, this is an inverse, so this is 1 over, right? So multiply both sides by this, right? And then we get this right here. And then I just make this x just so you can see that it's data, right? So we have this, and then you just bring the log through, right? This becomes a plus and a summation. So we have this. So this is A. That's our original equation. So how do we train? For training, we apply all of our maps to Z naught to get ZK, and then we compute this term. And then we add up. Once we get ZK, we add on this term. And then we just back propagate on whatever the loss is to train our thetas. And now the problems with this discrete normalizing flows, the problems with this equation is the determinant and also f. F has to be invertible, so it makes it challenging, right? There are a lot of neural networks that aren't invertible. So you have to have special types of neural networks that are invertible, and also computing determinants for large Jacobians is very expensive. So you have to have approximations to the Jacobian, which also hinders you. And so, yeah, that's discrete normalizing flow. So basically, next in the series is conditional normalizing flows, which basically they try to solve some of these problems. So basically that's it. So I think the important stuff to know is, in order to get that formula, we need the conservation of probability mass. We need to understand how the determinant of the Jacobian is a scaling factor for the area in the original space. And then we use those two facts together to we do some algebra here, and then we swap in this here, and we get this form. And we also know that it extends to higher dimensions, right? So this is our general form. And we just expand out the recursion here. We just define all of these probability density functions of Z1 and Z2 using this general formula. And then I substitute, this into here. And then we get this product, multiply both sides by this to get this. And then I just replace Z naught with X so you can see explicitly that it's data. And then I bring the log through. And so this is our loss function, right? Is our loss function. And then we make it negative log likelihood for backpropagation. So there you have it. Let's stop this video here.